Sampling theorem. So today we are going to discuss about sampling theorem. So in sampling theorem, a continuous time signal can be completely represented in its samples, and again it can be recovered back if the sampling frequency is greater than or equal to the twice of the highest component of the message signal. That means in sampling theorem states that the continuous time signal can be completely represented in its samples. Again, the continuous signals can be recovered from the samples if the sampling frequency is greater than or equal to the twice of the highest component of the message signal. So this is the condition for the sampling theorem. Fs greater than or equal to 2 into Fm. So Fs is the sampling frequency and Fm is the message signal. It's a maximum frequency of the message signal. So the sampling frequency should be greater than or equal to 2 into Fm. Next here x of t. So is the example signal or message signal having sine 2 pi t plus sine 3 pi t plus sine 4 pi t. It's an addition of three signals. First signal sine 2 pi t and sine 3 pi t. Last one sine 4 pi t. So this message signal Fm is the frequency or maximum frequency of this signal. So we are calculating the frequency for each and every signal. So first omega 1 equal to 2 pi. So from this 2 pi f1 equal to 2 pi. So from this f1 equal to 1. Again for this signal omega 2 equal to 3 pi. 2 pi f2 equal to 3 pi. Again f2 equal to 3 by 2 equal to 1.5. And for these signals omega 3 equal to 4 pi. So instead of omega 3 we are writing 2 pi f3 equal to 4 pi. So f3 equal to 2. Next the maximum value of the message signal equal to maximum value of f1, f2 and f3. So next it's a diagrammatic representation of sampling theorem. So here's continuous time signal. So this is a continuous time signal. It's having the amplitude and the time. It's having continuous time. Again this is a unit impulse train. So the unit impulse train or the sampling function, it will be indicated by s of t equal to del of t minus n into n times ts. Again this is a sampled signal x del of t. So the continuous time signal and unit impulse signals are added. We are getting the sampled signal x del of t. So this is a continuous, the signal will be in time domain x del of t. Now let us see the mathematical expression sampling theorem. So first step, represent the sampling function x of t mathematically. So the sampling function is nothing but unit impulse train signal. S of t equal to del of t plus 2ts plus del of t plus ts plus del of t plus del of t minus ts plus del of t minus 2ts. So it's having negative sides and positive sides. The unit impulse signal. So S of t equal to, we can written as sigma n equal to minus infinity to infinity del of t minus n times ts. Again represent the sampled signal x del of t mathematically. So x del of t will be in time domain. X del of t equal to sigma n equal to minus infinity to infinite x of n into n times ts into del of t minus n times ts. So here this is a continuous signal and this is a impulse train signal. We are adding this, we are getting the sampled signal, but the sampled signal will be in time domain. Third step, obtain the Fourier transform of sampled signal. So x del of f, we are applying Fourier transform to convert the sampled signal from time domain to the frequency domain. X del of f is the frequency domain, equal to fs into sigma n equal to minus infinity to infinite x of f minus n times f of s. Next, fourth step, the sampled signal x del of t completely represent x of t. So they have proved. So next one, the represent x of t as sum of synchronized function. So x of t equal to sigma n equal to minus infinity to infinite x of n by 2w sine 2 omega wt minus n. So this is the graphical representation of interpolation process. So this is a sampled signal x del of t and this is a reconstructed signal. Again, by using ideal low pass filter, we have recovered x of t. Here x of f is the sample function having the frequency minus, having the bandwidth minus omega to omega. And here x of del of f, this is the sample frequency in frequency domain having the bandwidth minus w to w, and these are the low frequency component. It's having the center frequency of minus fs and these are the bandwidth minus fs minus w minus fs plus w. And this is the signal at the output of the reconstructed filter. Again, with the help of low pass filter, the original continuous time signal is recovered. Okay, so this is the process of sampling theorem. So in sampling theorem, the continuous signal is converted to the sampled signal. Again, from the sampled signal, the continuous signal is recovered. The condition is the sampling frequency is greater than or equal to twice of the maximum value of the message signal, maximum frequency of the message signal. Okay, thank you.